Hi, everybody. So we're going to get started. Today we're going to have a guest lecture from Mohammed Narouzi, who's going to tell us about how supervised learning and reinforcement learning might interact to produce new and better reinforcement learning algorithms.
Thanks. Thank you for coming this early in the morning. So the idea of unifying supervised learning and reinforcement learning is a very ambitious goal. So I'm going to scratch the surface of that topic a little bit, hoping to get to better unification later on. This is joint work with Ophir Nacham and Dale Schurmans and a whole bunch of people on the BRAIN team. Ophir is a BRAIN resident on the BRAIN team. He was at the company before, and then he started doing deep learning research as a resident. And he's been very productive. I'm just using this opportunity to tell you guys that the residency program at the BRAIN team is a good place to do a one-year open research in collaboration with Google BRAIN folks. OK, so when I took a graduate machine learning course, basically the instructor would skip the reinforcement learning section, saying that somewhat it's not too relevant. And over the course of last several years, reinforcement learning has become more and more relevant. And I think nowadays, any machine learning researcher who doesn't know much about reinforcement learning should basically try to catch up. And I actually went back and checked the Chris Bishop book, which is a standard book for machine learning, for references to the term reinforcement learning. I only found several references only in the introduction, and not many discussions about, for example, expected reward, or how this connects to structured output prediction. And I was surprised. But also, if you go and check the reinforcement learning book by Bartow and Sutton, you probably see that they have their own clique, and they don't reference a lot of work from outside reinforcement learning community, and they use their own terms. So my goal in this talk is to try to unify the two paradigms and discuss approaches that basically take bits and pieces from the two paradigms and combine them to approach hybrid problems. OK, so I want to start by asking a question. What is the biggest difference to you guys? What do you think is the biggest difference between supervised learning and reinforcement learning?
It's interactive.
OK. Reinforcement learning is interactive.
You have an ideal y, so your loss function is relative to that ideal y. So there's an ideal label for each.
In supervised learning?
Yeah.
OK. You wanted to say something?
In supervised learning, generally your data comes from IID distribution. But in reinforcement learning, the distribution of your data is determined by your current model.
OK. These are all good points. And I start by saying that the problem domains are definitely different. But one can think of both approaches as learning a mapping from inputs to outputs, or from states to actions. So it's really a mapping. And to me, the key difference is the objective function. So over the course of presentation, I'll describe how the objective function used in reinforcement learning is different from supervised learning. And when I say supervised learning, I really mean a structured output prediction, where we are learning a mapping from inputs to multivariate correlated output variables. For example, image captioning or translation. And the objective often used in supervised learning is conditional log likelihood. So I'll try to describe that later on a bit more specifically. And when I use the reinforcement learning term, I refer to discrete actions, deterministic environments, and finite horizon problems. The finite horizon case will be a bit vague in some situations, and we'll talk about infinite horizon too, but the objective function is often expected reward. And the key that connects the two objectives is entropy. So you can try to optimize expected reward by drawing samples from your policy and being greedy about it. But what you should be concerned about is falling into a local minima, basically exploitation. And that means the model is super confident about its predictions. Now, entropy is a measure of uncertainty in the distribution, and adding the entropy to the expected reward objective allows for better exploration, basically forcing the model to not be too confident early on. But turns out adding the entropy, incorporating the entropy in the objective, allows us to see the connection between the two paradigms more clearly. Let me start by the image captioning example to allude a little bit more to the similarity between the two approaches. So let's say we want to learn a mapping from an image X to a sequence of words boldface A. So I'm going to use boldface A to refer to a vector of actions. And we want to learn this mapping. Now, if this is a supervised learning setup, we would have a lot of input-output pairs, as some of you mentioned. And we just try to incorporate those pairs into our parameters of the model. In the reinforcement learning setup, one can think of having access to some radars that measure the reward of a sequence of words given an image. So I don't have necessarily a sequence of ground truth words, but I have access to human radars or some measure of reward. And what I can do is that I can generate sequences and I can evaluate them. And really, in real world, we have a hybrid of the two paradigms. Like, we never basically just do trial and error when we learn. We often have teachers or parents who tell us about some things. They teach us how to walk. They teach us how to talk. And the idea of just using trial and error to learn complicated mappings, to me, is very weak, and it's not going to succeed in the near future. But when we combine it with the idea of having expert trajectories and the labels, then it becomes all of a sudden more powerful. And I think really we want to be able to connect the two paradigms to solve real-world problems. OK. I may have a bit more equations and stuff in this talk. Sorry, it's a bit technical. It's early in the morning. If you haven't waken up yet, wake up. So we want to learn a mapping from X to A. X may be a sequence itself and may become clear through the course of predicting actions. And we have boldface A, which is a sequence of actions. And for the beginning of the talk, let's suppose we have a non-decomposable reward function R of A, given X. Now, we have a policy or model in both structured prediction and reinforcement learning, which is a product of each action given previous actions and previous observations from the world. OK? And for brevity, I'll just drop all the conditionings on X. OK, so we have a distribution over action sequences, and we decompose that distribution using chain rule as a product of each action given the previous ones. Now, I'm going to introduce a distribution over actions, which is super important. By the way, this is just a roadmap of the talk. All the details will become more clear after on. This distribution I call the soft optimal policy. Okay. If I wanted to optimize expected reward, what is the optimal policy? The optimal policy is a one-hot distribution that has a probability of 1 on the correct action and probability of 0 everywhere else. I'm assuming discrete actions and finite set of actions. But that distribution is really hard to work with. So what we do is that we make that distribution soft by using this Boltzmann distribution, which is defined in terms of a temperature parameter tau. The temperature parameter tau is really important here. So as tau goes to 0, this soft optimal policy converges to the one-hot distribution, the optimal policy. And as tau goes to infinity, this soft optimal policy converges to uniform. So we have no reward, essentially, and we only have entropy. Now, what I'm going to show you later on is that conditional likelihood, the typical objective of structured prediction, is a KL divergence between the soft optimal policy and my model, defined in terms of a compositional model, product of terms. And the expected reward objective is a KL divergence in the other direction. But the typical scenario is defined at temperature 0. So it's really hard to see the connections. But you really see the connections when you actually let the temperature to be non-zero. Now, throughout the talk, I'm going to color the optimal policy blue. So wherever you see a blue distribution, that's fixed. Okay? And our goal is to try to find the blue guy. Basically, we want to learn the parameters theta so that they approximate the blue guy. I think I'm wearing blue too. Now, the key question is, how are we going to find the blue guy? And that is through a divergence or a distance function. Now, here I mentioned 2 examples of divergences. But a very interesting research question to me is to find even more interesting divergences. So if the goal is to find this soft optimal policy, there is the optimization issue, local minimas, and rate of convergence and stuff. So different divergences may behave differently in the speed that they basically converge to the optimal, if they ever converge to optimal. OK. Now, my talk has 3 pieces. I'm not sure if I get to the last piece, but I hope so. In the first piece, I'm going to discuss a conditional log likelihood objective at a temperature larger than 0. And I call that objective reward augmented maximum likelihood. I'm just giving you an idea of the whole talk. And then in the second half of the talk, I'm going to argue that combining the 2 KLs allows us to do better exploration. So the idea is that the KL between the model distribution and the optimal distribution is mode seeking because it samples from the model distribution. And the KL between the optimal policy and model distribution is mode covering because you're sampling from the optimal distribution. And finally, in the last part, I'm going to focus on the composable rewards, which is a typical case in reinforcement learning. So we're going to observe rewards as we do the actions, and the total return is a sum of discounted rewards. And I'm going to show how incorporating entropy within the typical Q-learning is giving us a notion of softmax backup. Softmax in the sense of log sum x. OK, let's start by a quick review of KL divergence and entropy and such things. I'm pretty sure you have a good background of that, but I just wanted to start there to make sure we are on the same page. So entropy measures uncertainty or information content of a distribution P. Now, in the discrete case, it's easy to write. It's basically summing over all the action sequences and multiplying the policy by log policy. And you can think of that as an expectation of negative log P. Because P is always between 0 and 1, negative log P is always positive, and entropy is larger than 0. Now, it's a concave function when it's defined in terms of a simplex, and it obtains the maximum uncertainty, the maximum entropy, when we have a uniform distribution. In that case, we have sum of 1 over n, log of 1 over n, and basically the sum goes away, and we get log of n. This is measuring the number of bits of information that a random sample from the distribution conveys on average. So if I have n outcomes, I can represent them in log n bits. And in the uniform case, because I have no prior, I need log n bits to communicate the uncertainty. Now, at the minimum, when I have a one-hot distribution, the entropy is 0. So now you should have an idea of why adding the entropy takes us away from the one-hot optimal policy. Because the one-hot optimal policy has the smallest entropy. So if we add some entropy to our objective, if we encourage entropy, then the optimal policy will not be one-hot, because that's basically the worst distribution in terms of entropy. And here I'm plotting an entropy of the Bernoulli distribution for 2 outcomes as a function of probability of one of the outcomes. And the maximum is 1, and the minimum is 0. Now, KL divergence is defined as a measure of discrepancy between 2 distributions P and Q. Let's suppose these are 2 distributions over our action sequences. Throughout the talk, any objective that I write, I try to maximize it. And for that reason, I write KL as negative KL. So if we maximize KL of P and Q, basically, if we maximize negative KL of P and Q, we get P equals Q. So I'll get to that. But the KL is defined as a sum over all the action sequences of probability of A, the first argument of KL, times the difference of log probabilities of the 2 distributions. Now, you can think of this as an expectation with respect to the first distribution of the difference of log probabilities. And negative KL will become entropy plus some notion of negative cross entropy. Basically, an expectation with respect to distribution P of log Q. OK, so KL is non-negative. You can prove that by Jensen inequality. It's asymmetric, as you see already. So we are doing an expectation with respect to the first argument. And it's 0 if and only if the two arguments are equal. And one characteristic of KL is that I can ignore the normalization constant of the second argument as long as it's constant. So if we go to the definition, the expectation with respect to P of log Q becomes log Q prime negative log Z, and I can take log Z out of the expectation. And if log Z is a constant, then it doesn't matter. Now, finally, one of the most important intuitions is that in one direction, KL is mode covering, and in the other is mode seeking. This image is taken from Chris Bishop's book. And here, we have the blue distribution as our optimal distribution, and we are optimizing the red distribution. Now, in the first case, the blue distribution is on the left-hand side of the KL. So we are sampling from the blue distribution, and we are measuring log of the distribution Q. So if the distribution Q doesn't appreciate some modes of the distribution P, we are in trouble because log Q will be very negative, right? So let's say Q is 0 on one of the modes. In that case, log Q will be negative infinity, and basically the loss is really bad because in this case we are minimizing. However, when the blue distribution appears on the right-hand side of the KL, we don't care too much about mode covering anymore. So we have a notion of entropy of distribution P, but other than that, we just want to sample from distribution P, and we want to see large values of log Q. And my earlier point about the partition function is really important here, because when I sample from distribution P, I may not have an understanding of distribution Q at all. So when distribution P is defined in terms of the middle figure, the red Gaussian in the middle figure, basically the distribution very occasionally samples point on the other mode of the KL. Now, the issue is a bit more subtle here because my assumption was that the distribution that is being optimized, the red distribution, is unimodal, whereas the actual optimal distribution is bimodal. So we cannot have a KL of 0, right? We cannot get a KL of 0 because we cannot have a unimodal distribution matching a bimodal distribution. But in reality, when we use neural networks that have a lot of expression power, then we can potentially have exact 0 of the KL. But there is another issue, and that is the issue of local minimas. Even if I have a very expressive model, when I use KL between the red distribution and the blue distribution, my intuition is that there are a lot of modes in the objective, and you can easily get trapped into local minimas, whereas in the other direction, at least when you optimize with respect to logits, the log probabilities, the objective can be convex. OK. Any questions so far? Yeah, sorry. The first part was just trying to get some of these basics straight. But if there's no question, we can go to the first part. So in the first part, I'm going to discuss this algorithm for supervised learning, and the motto is to learn from good mistakes. So basically, in a lot of supervised learning algorithms, we just have a correct output sequence, and we have a whole bunch of wrong sequences. So we penalize all the wrong sequences equally. But not all wrong sequences are the same. So the model should be able to learn which one of the wrong sequences is actually better than the others. And that is the key intuition that led to the development of this algorithm. OK, so if you're a vision person, image segmentation is your example of structured output prediction. If you're an NLP person, machine translation would be a canonical example. And we can have a mixed NLP vision problem of image captioning. In all of these cases, we have potentially lots of input-output pairs to train on. We have outputs that comprise multivariate, correlated, discrete variables. And given a complete output, we can measure the reward signal, which in the image segmentation is usually intersection over union with respect to ground truth. In the machine translation is blue or sometimes rouge score, mostly for summarization. And maybe for image captioning, you want to go with human evaluation. So we really have reward signal in structured output prediction too. But usually, the sort of dominant approach nowadays ignores the reward signal and simply optimizes a conditional log likelihood. So in this approach, the output is defined as a sequence of decisions. OK? So if I'm predicting a sentence, at every position, I make a decision what word to pick. And each decision is dependent on the early on decisions. So we can even select an arbitrary order on the variables. For example, in the image case, it's less clear what the order should be. And we define the output as a sequence of decisions. And we again define our model in terms of a chained prediction model. And we simply optimize the log probability of the ground truth output given the input. So I use A star to denote ground truth sequence. And A is just an arbitrary sequence. So this is conditional log likelihood, right? Now, at inference time, we usually do beam search to find an approximate argmax of the probabilistic model. So we want to find the most likely sequence according to the model, and then we measure the reward of that prediction versus ground truth sequence. So for example, this reward may be blue score or intersection over union or things like that. And the model that's used quite often these days is a sequence-to-sequence model where if I'm doing translation, my input is a sequence also. If I'm doing image captioning, maybe I just have a inception or VGG network to basically create some features. And one interesting idea in this type of model is this idea of having variable length. So my sequence may have different length, and to handle that, they introduce this special token of end of sequence. So we feed in ground truth variables during training, and we measure cross entropy of the prediction versus ground truth prediction, right? So the model is really producing probabilities conditional on correct output prefixes. Okay. Now, let's drop the conditioning on X again, and let's only think about a single example. The conditional log-likelihood objective can be written in this form, right? Again, I'm maximizing the log probability of the correct sequence. And I can write this conditional log-likelihood in terms of a KL divergence between a one-hot distribution that is putting a probability mass of 1 on the correct sequence and 0 everywhere else. Okay? And the entropy of this distribution is 0, so the constant is 0, basically. So have entropy times cross entropy, which is basically this objective. Now, in this objective, there is no notion of reward, and all the negative sequences are equally penalized. There is no notion of good mistakes. And if the model does very well, it will overfit to output sequences. It will memorize the exact sequence. Now, there has been some effort in applying reinforcement learning to structured prediction, which is basically you try to optimize expected reward with respect to the model. And I'm advocating to add the entropy term too. So this is not introduced by me, but like it has a long history in reinforcement learning. But we'll get to that later on. But so I could either multiply the entropy by the temperature parameter, or I could divide the rewards by the temperature parameter. But it's more convenient to divide the rewards by temperature tau, if you don't mind. So this is the entropy regularized expected reward objective, originally proposed by Peng and Williams. But Jeff Hinton also pointed out that he had a discussion of it early on as well. Now, to optimize this objective, we can use policy gradient to sample from the model to generate sentences and then evaluate their rewards and then weight the gradient of log probability by the rewards. Now, it's known that the gradients are high variance and training is slow. But really, if we optimize structured prediction this way, we are not using supervision as much. So the only way that supervised labels are being used in this approach is in the definition of reward itself. And the model is just trying to find those supervisory signals. So to make this work, people often initialize the model with a conditional log likelihood objective. And the problem is, after you initialize with conditional log likelihood, you basically diverge very fast, and you forget all the supervision very fast. So my intuition is that this is not the most efficient way of making use of labels. But let's get to the key observation. So the key observation is that in the presence of entropy, the expected reward objective is really a KL divergence between this blue guy, between the model distribution and this blue guy. Okay? And the blue guy is the soft optimal policy, the Boltzmann distribution. Okay? So if you remember, the KL was just entropy plus expectation with respect to the first argument of the log of second argument. Now here, the second argument is simply pi star sub tau And log of that guy is really reward divided by temperature minus log z. Okay? And log z is a constant here. What is log z? Log z is simply summing over all the reward temperature scale rewards over the space of sentences, right? So that's a constant. So you should be convinced that when I optimize expected reward with entropy, I am just optimizing this KL divergence, right? Is that clear to everyone? And now, what is the most basic thing to do? Now, going back to the idea of mode seeking versus mode covering.
Just go to the peak.
Sorry?
It would try and find the peak.
This guy is probably going to find a mode, and which may not be the peak, and may fall into local minima. But how can I mitigate that? Yeah, and that's basically what we did. So what we said was that how about optimizing for the optimal policy pi star more directly through the other direction of KL? And basically, when we reverse the KL, what we're going to do is that we're going to sample high reward sequences, and we're going to try to increase their log probabilities. So it's much more direct. So in the temperature of 0, I'm going to only sample ground truth sequences, and that is ground truth targets, and that is conditional log likelihood. But when temperature is larger than 0, I'm going to generate some augmentations around the ground truth target as measured by the reward distribution and this by the reward function and this Boltzmann distribution. Now, basically, I can ignore the entropy of the soft optimal policy because that's constant, and I simply get an expectation with respect to the soft optimal policy of log pi theta. So this is similar to conditional log likelihood in the direction of KL, but it's similar to maximum entropy expected reward objective in its optimal policy. So both of these two directions of KL, if I have a very expressive model, will converge to the same objective. And we have a notion of reward in the objective as opposed to conditional log likelihood, which is basically the way I'm doing the augmentation, the way I'm sampling these target sequences. And as temperature goes to 0, we recover the one-hot distribution, and the temperature is really controlling the concentration of the optimal policy. Now, one additional property is that this objective is convex in terms of logits of the neural network. And you can show that as a homework.
So there's something a little funny here, right? Because KL divergence is convex in the first argument, as is any fragment divergence. So how does parameterization play into this? Because it's clear that that kind of objective is actually easier to optimize, but that seems to not quite square away with the notion that KL divergence is convex in the first argument.
That's actually a good point. So KL divergence is convex in the first argument, but the first argument lives on the simplex. So if I had a tabular problem, And if I wanted to represent the distributions in terms of their probabilities themselves, then the KL would be convex in the first argument. But the problem arises when I represent the distribution in terms of logits. So basically, my parameters are now the log of the distribution. And in that case, you can even see that entropy is not concave anymore, because entropy is bounded above and bounded below. So if you define these parameters, so let's even think about a very simple case of a Bernoulli distribution when I have theta and I have a sigmoid defining my distribution. Now as I go to infinity, my entropy goes to 0 because sigmoid is saturated. But really, you get such a shape which is not convex anymore. Now, there is a more intricate notion here, which is, as you alluded to Bregman divergences, there is a conjugate of the function of which you define the Bregman divergence. And when you define the conjugate, then you define it in terms of logits, and the two directions flip, the two arguments flip, and then it becomes convex in the second argument. Anyway, but yeah, so if I were to parameterize my distribution in terms of probabilities themselves, yes, it would be convex, but I'm really representing my distribution in terms of the log of the distribution. All right, so just to wrap up, the way we train models with this reward augmented maximum likelihood idea is that given a pair of X and A star, we first sample one augmentation, and this augmentation is conditioned on the ground truth sequence because the reward is defined in terms of the similarity between A star and A. Okay? And once I sample A tilde, then it's very much like supervised learning. It's very much like conditional log likelihood. So you can think of this as a form of data augmentation and a smoothing of the distribution. And in practice, we just sample one augmentation per input, per iteration, and we don't need to do any bootstrapping. One thing to note is that if I only have a single example, it's very easy to overfit with conditional log likelihood. The model will just memorize the sequence. But it's much harder to overfit with reward augmentation because the model has to learn the distribution of glue score or edit distance or something like that. The model has to realize what mistakes are good and what mistakes are bad, how the distribution is shaped in the sequences. And that is a very good way of preventing overfitting when the data sets aren't so big. By contrast, if I were to use reinforce, I would sample from a non-stationary distribution pi theta that is being optimized, whereas the pi star distribution is stationary, and that's fixed. So you can even cache samples from pi stars and even run more expensive MCMC type algorithms for doing it. Now, in our examples, we really hacked the sampling from the soft optimal policy. Because really the key technical piece here is that how can I sample A tilde from the soft optimal policy? And that can be quite tricky. For example, for blue score, I don't know how to do it. But for negative Hamming distance, because it's a reward, I'm defining it as negative distance. For Hamming distance, what you can do is something called stratified sampling. So there are how many possible Hamming distances? Not very many, right? The number of buckets of Hamming distance is really the number of tokens plus 1, right? So I can first count the number of sequences within each distance, and then I can compute the partition function that way too. In other words, let's just suppose the sequences are of length m, and let's suppose we have a vocabulary of size v. Okay, so the distance is in the range of 0 to m. The reward is in the range of 0 to negative m, and all the sequences at the distance of k are simply m choose k. I first need to select the tokens that I want to flip, and then for each one of them, I have v minus 1 choices. So I can really do a simple counting and then compute the normalization factor. For edit distance, it's a bit more tricky because you can delete and insert, and you may have duplicates and double counting. So in our paper, we have an approximate sampler that works well. In the blue score case, I don't think it's easy to design a exact sampler, but one can do MCMC. And you should see a connection between this and simulated annealing in some way. So you can try to do metropolis Hastings by navigating the reward landscape, basically proposing a new sequence and then rejecting it if you don't like it. And the samples can be pre-computed. So we didn't spend much time on the MCMC variant, but in the second half of the talk, I'll be talking about a form of doing importance sampling to approximate sampling from the exact soft policy distribution. Now let's go to results. So in this case, we used edit distance sampling. So we have exponentiated negative edit distance as our soft optimal policy. And TIMIT is like the MNIST of speech recognition. It's a relatively small data set. And the results are, the best results, I think, are in the range of 17 phone error rate or something like that. I think their speech folks have gotten further down, but the machine learning approaches are in that range of phone error rate. So here we report the phone error rate on the def set and test set, and we also report the minimum and the maximum of the phone error rate and the average for 4 training runs. It can be a bit different because of the size of the data set. So we ran it 4 times on average. Now what we observe is that as we increase the amount of augmentation, the phone error rate keeps getting better. So the best phone error rate that we observe is at a temperature of 0.9, which is about 2 to 3% improvement in terms of for phone error rate. And we also see a consistent improvement from a temperature of 0.6 to a temperature of 0.9, and then it falls off. But what's more interesting is to look at the amount of augmentation, right? So what do I mean by temperature of 0.9? Well, here I'm plotting a distribution over number of edits for a sequence of length 20. And what I observe is that at a temperature of 0.9, augmentations with 5 to 9 edits are sampled with a probability larger than 10%. So really, I'm doing a hell lot of augmentation. And I'm potentially not sampling the ground truth sequence at all, because the probability of sampling the ground truth sequence is so small. But it does much better, and it generalizes much better, which is really interesting. Now, we also did some experiments on WMT translation, and this is in terms of blue score. We didn't have a way to sample from blue score, and we didn't think about Metropolis Hastings back then. So here we're just sampling from Hamming distance. And you can see it doesn't do as well, but you still see that the blue score goes up, and then it falls off, and you again can visualize the number of augmentations, and it's quite a bit of augmentation. I wanted to point out that this has some similarity with label smoothing work for classification, where instead of trying to optimize cross entropy with a one-hot distribution, you basically set the probability of a mistake to be 1 minus epsilon over the number of classes. And so, for example, for MNIST, you can say, I want the correct label to have a probability of 0.1, correct label to have a probability of 0.91, and I want everything else to have a probability of 0.01. And that is the special case of reward augmentation for classification. Also, after the paper was published, we figured that there was a work by Rich Semmel, Hugo, and Max Wolkoffs on a relatively similar approach applied to conditional random field. They didn't have the connection with reinforcement learning, but they were also doing this sampling from the Boltzmann distribution. In their case, the problem is much simpler because they are in a tractable setting where the number of alternatives isn't that large. I also wanted to mention a set of papers which try to optimize basically expected reward they try to optimize some form of reward by sampling or inference during training from the model. These methods are generally more expensive because they need one pass of forward propagation to sample and then use the samples for training, whereas in our case, we just deal with the reward itself. All right. Now, the question that we had after doing this work was, how can we apply this to reinforcement learning?
I was just going to ask before you go in, if you could talk also a little bit about the relationship between this and like structured margin or softmax margin methods, because it seems like you have effectively white box access to the reward function.
Yeah. So in general, in structured prediction approaches, you come up with an upper bound on the loss itself. And you optimize this upper bound. Now, in linear models, where I have W transpose psi of x and y, the upper bound is convex, and it's very convenient to optimize. But when we go to neural networks, the upper bound doesn't have the convex characteristics. And it's also not very clear how tight the bound is. So as far as I know, there has not been a lot of success applying structured prediction to sequence type models where the output is very high dimensional and complex. But that can be because people haven't done much exploration with that, or I'm not sure. But the more subtle similarity, I think we need to discuss about it offline, how the two approaches exactly relate. But the key difference to me is that those approaches usually come up with an upper bound, whereas in this case, we have an approximation and we have this basically guarantee about the optimal policy of the objective. OK. Any more questions?
Yeah, so when you're using the temperature variable, do you have to like schedule it at all? Like, it can there be an issue where the temperature is kind of not appropriate?
That's actually a good question, and I'll get back to that hopefully in the second half of the talk. But in the supervised learning case, it seems to me that we may actually not want to drop the temperature to 0 because that would result in overfitting. So if we are using temperature as a way to combat overfitting, you may not want to annihilate to 0 because once you annihilate to 0, potentially you overfit. But in the RL case, if the goal is to optimize expected reward, and if that's your real objective, and the entropy is just a term to help exploration and mixing, very much like simulated annealing, then yes, you would want to anneal the temperature. OK, so the second part of the talk is about this technique called underappreciated reward exploration. And we came up with this acronym UREX, basically inspired by T-Rex. Now, the idea is that when we discuss this soft optimal policy, right, exponentiated reward, we really have this connection between value and policy, right, between rewards and policy. So rewards live in a space where entropy lives, and then you exponentiate them and normalize them, and you get the policies. Now, if I have a bunch of action sequences, and I have a bunch of log policies, I may want to match them with rewards themselves. Okay? If I really believe in this soft optimal policy. The soft optimal policy is when basically log policies are shifted reward over temperature values. The key issue is the partition function itself, right? The log z is the shift. But if I have a bunch of samples, I can try to match them, and I can try to come up with an approximation of the partition function. And this is related to importance sampling. So if you missed the first half of the talk, don't worry. Wake up now. I think you'll be able to catch up. So the motivation here is that common forms of exploration in RL are undirected. For example, you can do epsilon greedy, where you just uniformly sample a random action. Or you can do entropy. Entropy is also very undirected because it's just more uncertain, the better. But it doesn't care about how the uncertainty is distributed and how it's related to rewards, right? And the motivation is we need better exploration in high-dimensional spaces because just undirected random exploration doesn't help much. And I think the count-based exploration falls into the same category of basically exploring everywhere. And I don't really think that that's going to succeed in very high-dimensional spaces with a sparse reward. Now, let's go back to the soft optimal policy. So the soft optimal policy, the blue guy, is defined in terms of exponentiated reward normalized across all action sequences. Now, from the intuition of KL divergence, we know that the KL divergence between the optimal policy and the model distribution is mode covering. So that should be a good exploration term for us, basically telling us to explore high rewarding regions, basically knowing the full landscape. So if I knew the full landscape, I would just sample promising trajectories, right? And that corresponds to the KL between pi star and pi theta. But I don't have it. So how can I sample from pi star? So that's the technical piece. But the key intuition is that we augment expected reward with this term, which is basically a constant plus KL divergence. Okay, so this is saying let's sample exponentially with regard to rewards. So let's basically very widely sample high reward regions, and let's make sure that the policy appreciates those high rewarding regions. And the key technical piece is to just do importance sampling, very simple importance sampling. We cannot sample from pi star, but what we can do is that we can sample from the model distribution, which is a set of on-policy samples, the model distribution that we are optimizing, and then we can do importance correction with pi star over pi theta. Okay? So, importance sampling. Let's talk about the baselines. The most naive baseline is reinforced, where we are trying to optimize expected reward, and the gradient of expected reward turns out to be another expectation of reward times gradient of log policy. And the way we do it is we draw KIID action sequences from the model distribution, and then we estimate the gradient by some form of Monte Carlo estimation. And we have a baseline to reduce variance. We can simply use sample mean reward to reduce the variance. Okay? So this is my way of presenting policy gradient. Now this fails even on simple problems, and that's not too surprising. It doesn't have much of an exploration term, and basically when it sees a large reward, it just sticks to it. I think it has some connection to the multimodality of this KL divergence in the mode seeking direction. Now, what if we augment the objective with entropy? If we augment the objective with entropy, so you can work out the math, we have pi theta log pi theta, and then we have the gradient of the first term and the gradient of the second term. It basically comes out as this. So we have an additional negative log pi, negative 1. Okay? Negative 1 corresponds to the gradient of log pi, and the log pi part corresponds to gradient of the sampling distribution itself. Now, if you want to estimate the gradient, again using Monte Carlo samples, you get this entropy bonus, which is saying if the model is certain about an action, that's bad. So whenever the model gets too certain about an action, it is penalized by negative log probability, right? And or it's probably more intuitive to think about it in the other way, which is whenever the probability is, the policy is very small for an action, then we have a large bonus. Okay, so we basically encourage the policy to be more uniform and less concentrated. This does better than reinforced, but still fails on problems with a large action space. And here is our proposal. So as I mentioned early on, we augment the expected reward objective with this KL term, or sampling from the soft policy and then measuring the log policy. So we again draw KIID on policy samples. And because we want to do importance sampling, we compute these importance weights. So these importance weights are proportional to pi star divided by pi theta. Okay, so I want to compute pi star divided by pi theta. I can write it as an exponential. Okay, and then we normalize the importance weights. So this is self-normalized importance sampling. And the way we estimate the gradients is by adding this Urex bonus term. So the W tilde values now sum to 1, because those are normalized, and the 1 over k values also sum to 1. So we really have two separate terms, one for policy gradient with the baseline, and one for Urex. And the key intuition here is that there is this notion of underappreciation. Okay? So if there is a action sequence that has a small reward, but the model assigns an even smaller log policy to it, it's bad. Okay? So we usually go about large rewards, and that's the expected reward term. We just sample large rewards, and we reinforce samples with large rewards. But what if we don't have quite that large of a reward, but the model is underappreciating it? That's very dangerous. So that is an indication that the model is ignoring part of the reward landscape. And that is really the contribution of the mode covering term. So these are the W tilde guys. So we really are comparing reward and log probability, and we're looking at all the samples, and we basically take the one that has the largest underappreciation and basically boost it up. Okay. And I already mentioned this, so it encourages exploration in areas where rewards are underestimated by the current log policy. And yeah, so the most underappreciated action sequence among the case samples will have the largest importance weight, normalized importance weight. And we need multiple samples to be able to normalize the importance weights, but it's super easy to implement. OK, so let's go through the experiments. So here we have an environment that is initialized with a random seed, and it provides us with some observations. Then we have an LSTM model that produces a probability over actions, and then we sample actions, we feed that back into the LSTM, and we give it to the environment, and the environment produces more observations. And at the end, it provides us with a reward. So the reward is non-decomposable, even though the tasks that we're working with have per-step reward, but we basically handicapped algorithms by just giving them the total reward at the end. And we again have this chained prediction model. So we applied this to OpenAI GYM algorithmic tasks. So in these tasks, you have a tape, and you have the actions of move left, move right, and you have an action of emission. Okay? So you observe the character to which you're pointing, and then you can emit or not emit and move left and move right. So copying is very easy. You just read and copy. All the algorithms learn this. So I'm comparing Urex with maximum entropy reinforce and reinforce. And duplicated input, I believe, is that you got to basically duplicate the input. I think the full sequence, then the full sequence again. But then things get more interesting when we go to harder tasks. So reversing, for example, you got to go all the way to the end of the sequence and then come back and start emitting. And you see that Urex starts to outperform both entropy regularized reinforce and reinforce. interestingly, we observed that entropy has a significant benefit, but it's not quite good enough for even harder tasks. So here we have reverse addition, where our tape has 2 rows now, and we got to add the 2 numbers, and then we can go up, down, left, right. And in the binary search, we created this task of basically querying a tape, and we have a bunch of registers, and we have the operations of averaging and shift right and +1 and stuff like that. So the model has to learn a notion of binary search by basically averaging the registers and looking there, and depending the outcome, it should go to the left or to the right. And in both cases, we observed that Eurex outperforms the other approaches quite significantly. Now, here we measured the hyperparameter robustness by changing the learning rate and by changing the gradient clipping among a bunch of options and by changing the temperature. Here we are again fixing the temperature, even though I think it would be useful to reduce the temperature. Now, for Eurex, we just pick a single temperature. What we are plotting here is that among all these combinations of hyperparameters, for 5 trials, I think each cell has 60 experiments, 5 trials of different hyperparameters, of different learning rate and gradient clipping. So this is measuring the success rate of the algorithm, because OpenAI Gym has this threshold of reward that basically tells the algorithm that it succeeded or failed. And we observed that Eurex has a much better hyperparameter robustness. So across the board, and we even only tried a single temperature. Again, we observed that reinforced doesn't do as well as meant, but Eurex outperforms both. And here, we only measure expected reward for the best setting of hyperparameters across 5 trials. And we again see a benefit. Now, keep in mind that here we are measuring expected reward. And expected reward is the objective of reinforce. However, these other algorithms augment the expected reward with some additional terms, but they get better expected reward. Isn't that a bit surprising? Now, people may just say, OK, that's because the gradients have high variance. You keep hearing gradients have high variance. But I think there is another part to the story, too, and that's local minimas. So when you add entropy, for example, you're increasing the basin of attraction of local minimas. And gradient descent optimizers have higher chance of success. Basically, but obviously, this is just a conjecture, because it's a bit tricky to show these things in a high-dimensional space. And it may be an interesting research project to try to really show it empirically that the reinforced objective has many more local minimas. Whereas as you add entropy, you have fewer local minimas. And the Eurex term also tries to use the other direction of KL to encourage the mode covering behavior and reducing the number of local minimas. And here we're just showing success rate. So basically, we can solve most of these tasks. But when problems get a bit harder, so there is a harder version of reverse addition where there are 3 numbers, and there is another version where the tapes aren't reversed, so you have to go to the end of it and then add the 2 numbers. And we didn't succeed with those. But with the next algorithm we did. Are we finishing at 10:30?
Yes.
OK, so I think we wouldn't have time to talk about the bridging the gap idea, but I just show you a trace of the algorithm adding 2 numbers. So it sometimes does wacky things, goes back to the same cell. And so you see where the pointer is, and the blue dots show where the emission has happened. And it's OK. And it also generalizes to longer sequences. So maybe 1/3 of the policies learned, they generalize to sequences of length up to 1,000. And here I show you the variance of importance weights as the number of steps. So at the beginning, the importance weights are very one-hot, because one of the sequences is underappreciated, and the rest of the sequences are OK. So when you really do this exponentiation in the importance weights, one of them get all the UREX bonus. But as you learn and as you converge to the optimal policy or a local minima, you observe that rewards goes up, but the variance of importance weights go down. So at the end of learning, most likely the UREX bonus has no effect because it's just uniform. So it's basically just adding a constant to everyone. So I'm not going to talk about this. Early on, I was pretty sure that probably we wouldn't have time to talk about it. But I can just show you this slide, which may be interesting. So in Q-learning, we are used to this max backup, where we compute the Q values over our actions, and we basically pick the best action and compute the reward and back that up. But it's not quite satisfactory. It's, again, very similar to this one-hot distribution. And with adding entropy, you get a softmax backup operator, which is, to me, much more satisfying, because now you have a knob to control the specificity of the max. So the log sum x at 0 temperature recovers max, but as temperature increases, you have a sort of more soft version of max. And most importantly, it gives us a way to connect values and policies. But we didn't talk about that. Yeah, so if I have like 1 more minute, I can mention that future directions include continuous control, because we focus on discrete actions, and continuous action spaces is something interesting, both theoretically and practically. The other thing is that in the third part of the talk that I didn't go over, we discussed entropy regularization with decomposable rewards. And now it's also interesting to think about UREX with decomposable rewards, UREX with induction. And that's probably a very interesting research direction. Incorporating trust region methods like TRPO into all these algorithms is interesting, and we already have some interesting results. And I'm quite interested in studying the connection between this entropy regularization and simulated annealing, and how, because I haven't seen the simulated annealing being much discussed in the reinforcement learning setup when it comes to falling into local minimas and stuff. And finally, we want to be able to exploit off-policy trajectories as well as expert trajectories into our algorithms. I think the softmax backup gives us a way to do so, but we need even better ways. OK.
All right. Thank you, Mohammed. So I think the instructor for the next course is not in the room yet, so we're not getting kicked out just yet, which means that if any of you guys have questions for Mohammed, I think we can talk for a couple of minutes if you guys want to ask anything.
Is there anything that kind of, this is about PCL, which you didn't cover, but like you mentioned that you're interested in applying it to continuous control. Is there anything that's kind of doesn't work right now for continuous control that needs to be change in the math, or?
I think actually the continuous case is related to one of recent papers of Sergey. I think there's a lot of connections between the two papers. Obviously, when we go into continuous control, one issue is that the soft optimal policy may not be normalized anymore. So, and there's also this issue of what is your prediction model? Are you happy with Gaussians with diagonal covariance, or do you want to make that? But I think the main issue is the soft optimal policy and the fact that you want it to be well defined.
Any other questions? Okay, well, so we'll have our last guest lecture on Monday, so Peter Abil will be speaking, and then after that we'll begin the final project presentations. Do note on Piazza we posted a sign-up sheet for slots for final project presentations, so be sure to sign up for a slot, and I'll see you all next week.